and welcome again to Chemistry 101. We are in Chapter 2 and we are in chemical formulas. Last time we've been talking about chemical formulas and different types of chemical formulas, including the molecular formula and the empirical formula, which is very important to apply into Chapter 3. We will continue our discussion today in chemical formulas, which are, by the way, are divided into basically two big categories. The first one is called inorganic compounds and pardon, the ionic compounds, and the other one is covalent compounds, and sometimes they call them molecular compounds. So molecular compounds, they're basically made of nonmetal plus nonmetal or a nonmetal plus hydrogen. An example is CO2, which is composed of carbon and oxygen, and they both are nonmetals, or CH4, which is methane, where carbon is a nonmetal and hydrogen. One part of molecular compounds is what we call organic compounds, which some people they actually refer them to as their own category compared with inorganic compounds. And these organic compounds contain carbon and other elements. Organic compounds are named, their big part. Organic compounds actually resemble a huge category in chemistry, and they are studied in organic chemistry courses, and they have their own nomenclature, and that's why we don't focus on organic compounds naming at this stage. Or inorganic compounds, they contain ionic compounds, which is a basic cation plus anion, so a metal plus non-metal. For example, NaCl, that's sodium chloride. Sodium is a metal and Cl is non-metal, and therefore it's an ionic compound. It includes also acids and bases and hydrates. So we're going to go over these categories one by one over this course. So the formula of ionic compounds consist of a combination of cations and anions. The formula is usually the same as the empirical formula, and this is important. That ionic compounds, we go with the empirical formula, but that does not happen to molecular compounds. And the sum of charges in the cations and anion in each formula unit must equal to 0. So the whole compound must be neutral. And let's take an example, NaCl. You might know that NaCl exists in a 3D network of atoms, as shown in the figure here, which we call a crystal. The crystal of NaCl consists of Na atoms connected to Cl atoms. And if this is one unit of a crystal, of course the NaCl itself is multiples of that shape that you see here. So if we're gonna make a formula for NaCl, we don't count the number of Na atoms and Cl atoms, and we say, okay, here we have 14 atoms of Na and 14 atoms of Cl, so it's Na 14, Cl 14. We never do that. We just take the empirical formula of that, which is NaCl, Na1, Cl1. So that's the idea behind naming ionic compounds. So as I said, ionic compounds, they're formed between metals or cations to the right, to the left, and anions to the right. Not only the group 1 and 2, of course, we can form ionic compound by any metal, including the transition metals. Now, how do we do formulas for ionic compounds simply? Let's talk about magnesium nitride. Magnesium nitride is made of two elements, magnesium and nitride, which is nitrogen anions. Magnesium is in group 2, so it's always making plus 2 ions. Nitrogen, as I said last time, nitrogen is a group 5, so it makes minus 3 ions. Okay, and that's important to remember the table that we talked about in the previous lecture. So here we have Mg2 plus and N3 minus. We can cross multiply these and remove the charges, and that will give us Mg3 N2 for magnesium nitride. So magnesium nitride is Mg3N2, nothing else. It's not MgN2 or MgN or something like that. And this is called the crossover method, and we're going to use it in this chapter. I think this question also asks about the same thing. So that would be the answer in the previous page. Now let's practice this in a few slides here. I prepared some questions for you guys. Let's apply this rule to write the formula for aluminum bromide. So there are two types of questions here. Either I give you the name of the compound and you give you the formula, or the other way around. Here I'm saying that aluminum bromide, so you need to figure out the formula of aluminum bromide. I know aluminum is Al, and it's a group 3, so it's always make 3 plus. Bromide means it's the anion of bromine, that's Br minus, and minus 1 because Br in the last group, in group 7, it always makes minus 1. So you can cross multiply this the 3 goes here, the 1 goes there, and you have Al Br3. That's the formula for aniline bromide. So if you have a multiple choice questions that ask you between AlBr2, for example, or AlBr, or whatever, Al2Pr5, that would be the correct answer. All of these are wrong because aluminum bromide does not exist in these forms. It's always AlBr3. One more, calcium sulfate. Now, what is sulfate? Some people they think it's S, but the matter of fact, it's not. Sulfate. So sulfate is SO4 2 minus. That's a polyatomic ion. Polyatomic ion that you need to remember. It's called sulfate, and it holds a charge of -2. And there are multiple polyatomic ions that you might remember from school or from daily life. There's something called SO3 2 minus. That's sulfide, not sulfate, but sulfide. You might know NO3 minus. That's one charge, one nitrate, like the ammonium nitrate that has exploded in Beirut a few weeks ago. NO2 minus, that's different, that's nitrite. You might know from your chemistry classes OH minus, that's common, hydroxide. So, and so on. There's a big list. There's acetate, sulfur, there's phosphate, there's phosphide, and the list is big, okay? And we're gonna remember this as we go. So let's go back to the question. So sulfate is SO4 2 minus. Okay, we know that now. So SO4 2 minus, that's sulfate. And we have calcium, which is Ca, and calcium always makes 2 plus. If you cross multiply this, it should give you Ca2SO4 all 2, but that's not the way to write down. We always simplify this in ionic compounds, so we write CaSO4, so that's calcium sulfate, okay? So in ionic compounds, remember, ionic compounds, you simplify. Only in ionic compounds. You don't do that in covalent compounds, okay? You don't do that in molecular compounds. Here we are given a chemical formula and we need the name. Well, that's easy. I know this is magnesium. Break this down into its ions. So this one is made from a cation called Mg2+, and there are nitrates there. It doesn't matter how much are they, because this is an ionic compound, so you call it magnesium, and this is nitrate. So here, this is the name. So in ionic compounds, we don't say dinitrate or 2 nitrates or anything like that. It's magnesium nitrate, because if I ask you what is magnesium nitrate, you should give me this, okay? So there is no mono or di here. These mono, di, tri, these acronyms are actually correspond to molecular compounds, so we never use them here. One more example, easy example, KNO2. The best way to know this is you need to know that this comes from K+. NO2 is a group, okay? It's called nitrite, NO2 minus, and you should know that it has one charge. So it's not. So you can name it potassium. Of course, you use the metal first, and you capitalize in English language the first letter of the paragraph. The other one does not have to be capitalized. So nitrite, nitrite. Okay. Not nitrate, but nitrite. Potassium nitrate is also actually a kind of explosive material. Anything that has nitrite and nitrates in it is kind of dangerous. So potassium nitrite is this one. So you never name it, for example, potassium nitrogen oxide. That's a kind of stupid name to name it. Potassium nitrogen oxide, no. You have to know that NO2 makes a group called NO2 minus, makes nitrate. So here we need to get into naming, okay? And naming chemical compounds is called nomenclature. Nomenclature means naming chemical compounds. So before you name a compound, you need to know that if it's either ionic or molecular, between brackets covalent. Don't mix the two. There are two different systems to name these compounds. We'll start with ionic compounds. So we'll take the first one, which is we call type 1 ionic compounds. Type 1 ionic compounds, they're made of group 1 and 2 only and any nonmetal. Okay, so this is here type 1. You take group 1 and 2. We can actually add Ag plus, Zn plus, and cadmium 2 plus to the, and also group 3. And we call this ionic group 1 or type 1 ionic compounds. So the group 1 and 2 and some elements from the transition metals as well as the aluminum group. And these ones, they don't change their oxidation numbers. Okay, they don't change the type of ions. So group 1 they always make +1. Group 2 they always make +2. Aluminum and gallium and indium, they always make +3. The zinc as well and the cadmium is known only to make 2+ ions, and that's why we combine them with the type 1. And Ag+, there is nothing else but Ag+. Ag silver does only make 1 ion. So this is type 1 ionic compounds, and you combine them with any anion, and that makes you an ionic compound. So that ion might be F-, called the fluoride, or Cl-, chloride, Br-, I-. Those are the halogens. So Br in the periodic table is called bromine, but when you make an anion out of it, it becomes bromide. And similarly, any other nonmetal, it's named the same thing. So oxygen is oxide, and sulfur is sulfide, and carbon is carbide, and nitrogen is nitrite, and so on. So this is how you name type 1 ionic compounds. This table is also this table is to be memorized actually, and this table as well. And here you have all the polyatomic ions that I talked about. So here you can see the carbonate, okay, cyanide, dichromate, all of these polyatomic anions. Here you have nitrate and nitrite, hydroxide, oxide, plus some other things that you might not hear about it before, like permanganate, MnO4-, phosphate, we know it, sulfate and sulfide. This is confusing. There's sulfate, SO4 2-, there's sulfite, which is SO3 2-, but there is sulfide, which is S2-, okay? And you see here the sulfate is written with an F, because this is an American textbook, and in UK they call it they pronounce it as with a PH. There's thiocyanide and so on. So anyway, you need to remember this table for the sake of naming chemical compounds. So let's through some examples of type 1. Again, you see these are all metals, Ba, aluminum, potassium, magnesium, and K. They are all type 1. So we can proceed and name them just easily. Barium, so the first one would be barium chloride, because it's Ba2+ and 1 Cl-. Here we don't use di and mono and those numbers, because this is type 1. We never use that in type 1 ionic compounds. So barium chloride is BaCl2, it's nothing else. I think we did this before, AlCl3, aluminum, maybe it was bromide, now it's aluminum chloride. Okay, the only thing I want to change in this is capitalize the A in aluminum and B in barium. K2O, so K is potassium, O is oxygen, so oxide, so potassium oxide. We don't say dipotassium oxide, that's wrong, just potassium oxide. Magnesium hydroxide for this one, and the last one I think we did it in the whiteboard. Potassium nitrate. KNO2 would be potassium nitrite. So that's type 1 ionic compound. Now, in type 2 ionic compounds, we deal with transition metals, and let me just explain this here in my whiteboard. So here we allow me to explain this in my whiteboard. Let's take FeCl3 and FeCl2. Well, FeCl3 is an ionic compound because it's made of a metal, it's iron, and a non-metal, which is chlorine. So I can name this iron chloride. But FeCl2 would be the same thing, iron chloride. Well, so in this case, iron makes more than one compound, and therefore more than one oxidation number, I would say, or different ions. So we need we need a system to differentiate between these two names. This is like two people, they're having the same name, or two people with the same ID. So we have to differentiate between these two by giving different IDs. I know Cl always makes -1. So this part of the molecule, Cl times 2 is -2, and this will make Fe plus 2. I know that halogens again makes -1, so this part of the molecule -1 times 3 is -3. So this part of the molecule is -3. That leaves Fe to be plus 3 ion. So in this case, I can say this, I can use Roman numbers. Which you know 1, 2, 3, so this is a 3, iron 3 chloride, and this is iron 2 chloride. You can put brackets, and this is type 2. It's still ionic, but this is type 2 ionic compounds, okay? So ionic compounds, you name them as before, name of the cation, and then a Roman number, and then the anion, or the polyatomic anion. And you use that for transition metals, because transition metals, as I said, they make different ions. For example, copper, it's known to make +2 and +1, okay? And manganese, it's known to make +2, +3, +4. So if you're given, again, a compound like that, let's say CuBr, now you can name this copper bromide, but if you do that in the exam, probably the teacher will give you 0, because that's not an acceptable name for copper bromide. Copper is a transition metal. It's not type 1. It's not a group 1 or group 2 or one of those metals that we consider type. This is type 2, and therefore you must use a Roman number for that. I know bromine is -1 all the time, so from this I can know that copper is +1. You see me here, I use the certain to know what is uncertain. I know that Br is -1, that's common. I use that to figure out the ion of copper, it's +1. Therefore, this is copper 1 bromide. And why do we do that? Because to differentiate between copper CuBr2, for example. CuBr2 would be copper 2 bromide. So these are the transition metals that I refer to, or the D block. The only exceptions, as I said, Zn and Cd and Ag, I take them out and consider them type 1, but everything else in this block, we refer to type 2 ionic compounds. So here are a few examples. We know that FeCl2 now, we call it iron 2 chloride, iron 3 chloride, we did that. MnO, any guesses? How do we name MnO? Mn is manganese, okay? So you can call it manganese oxide, but that's wrong, because you have to mention the Roman number here. I know that oxygen is -2, that will leave Mn to be +2, and therefore it's manganese 2 oxide. And this is exactly why we have to name it manganese 2 oxide, because there is another manganese oxide. It's the other one, Mn2O3. So Mn2O3 we need to know what is the oxidation number, or what is the ion, what kind of ion is this. Well, for now we can say that oxygen is most of the time -2, so -2 times the 3 is -6, so this part of the molecule is -6. That will leave us that 2 atoms of manganese will have +6 to make the molecule neutral, and therefore Mn would be equal +3 in this case. Or you can do this simply by doing some mathematics. You can say that you have 2 atoms of Mn, plus the 3 atoms times oxygen. I know that oxygen is -2. That should be equal to 0, because the whole charge on the whole molecule is neutral, is 0. So I'll give you 2 Mn minus 6 is equal to 0. And that will mean 2 Mn, I'll just put this one here, that will give you +6. And therefore you say, you divide both sides by 2 to get rid of this 2, and that will give you Mn is equal 6 divided by 2, which is equal plus 3. And therefore, this is manganese 3 oxide. Manganese 3 oxide. MnO2, that's another oxide for manganese, and you see here, manganese is indeed a problem. So in this one, we have 2 atoms of oxygen. Each one is -2, so minus 2 times 2 is -4, and therefore Mn is +4, and this will give you manganese 4 oxide using the Roman numbers. So this is copper with nitrate. You can call it copper nitrate, but that would be wrong again. You will be marked 0 if you name it copper nitrate. You should have copper 2 nitrate because of the fact there are 2 nitrates. Each one is -1, so -1 times 2 is -2. That will indicate that copper is a 2+ ion, therefore it's copper 2 nitrate. KH2PO4, that's not type 2, but here it's just for you to confuse you a little bit. You need to know that this is potassium, K. H2PO4 is a group called dihydrogen phosphate in the table that I showed you before. You need to know that H2PO4 is a group, is a polyatomic ion with one negative charge. So you just call it potassium dihydrogen phosphate. Here somebody asked me one day, teacher, why you're using this is an ionic compound using di, and you just said that we never use di and mono in this. Well, this is the name of a group. H2PO4 is called dihydrogen phosphate. So this is part of its name. This is how you name it, and that's why we still never use di and mono in ionic compounds. But dihydrogen phosphate is a name of a group, and we have to stick to that name. NH4ClO3. NH4 is ammonium, so that's a group. That's the only positive polyatomic ion. ClO3, it has a special name, which is chlorate. So you can call this ammonium chlorate without any dyes or monos. So that's a multiple choice question. What is the name of CR2, CR2O7, all 3? There are 5 choices here. I will leave you to think about this question on your own, and we can discuss this in class. And now we have a few questions here. Name the following compounds. We'll solve this in our whiteboard. Okay, so we have here A, which is FeNO32. If I am in an exam and I want to name compounds, the first thing I want to ask myself, is this ionic or covalent? This is ionic because it's a metal and polyatomic anion. Is it type 1 or 2? It's type 2. Okay, this is the way you do it. So type 2 means I have to figure out the number here. I know that this is made of Fe and some nitrates, and nitrates is minus, so I have 2 of them. 2 times -1, that will give us this +2. In this case, we can call this iron, and then 2 nitrate. I like to brainstorm things, and I just want to show you why. Some people will say, okay, this might be iron dinitrate. Of course, this name is wrong. And reason for that, first, this is type 2 ionic compound. We have to use Roman numbers to refer to the oxidation number of the metal. The second reason, we don't use di and tri. The other reason, there is no system on the wall that says you have to name it like that. Okay, so you have to stick with the system. The second one is Na2HPO4. The other one is Na2 HPO4. This one is made of Na plus ions. I can tell that. What is this? This is a group called this is HPO4, but you need to know the charge. This is 2 minus, and that's why it's taken 2 sodium. That makes sense. The 2 minus here takes 2 sodium atoms. This is ionic compound because it's made of metal or a cation and an anion. It's not covalent, and therefore I can just, and this is type 1, so there is no monodi. I can just name it sodium, and then this is called hydrogen phosphate. Hydrogen phosphate. That's the name of the group. Okay, hydrogen phosphate. Last one is NH4 that would be ammonium. Or actually, you know what? I will let you to do that by yourself later on. This is another question. Mercury nitrate, mercury 1 nitrate, okay? And there's something nice about, so mercury, so we have mercury 1 nitrate. So there's something about mercury I want to tell you about. It's interesting that you have to understand it. Mercury does two things. It does Hg2+, okay? And it also makes Hg2+. So the mercury 2+ is the mercury 2. Okay? Actually, this one, because there are 2 atoms of mercury and it has a charge of 2+, that means that the oxidation number of mercury in here is 1. So this is the mercury 1. When I say mercury 1, this is what is mercury 1, Hg2+. There is nothing called Hg+. This does not exist. Mercury 1 is Hg2+. So we agreed on this. Okay, and nitrate is NO3-. So now I need the formula of this. I can cross multiply. So this is +2. The whole thing is +2. This is -1. So I cross multiply. That will give us Hg2 NO3 all 2. So that would be mercury 1 nitrate, Hg2 NO3 all 2. I cannot. This is a special case here, that this one I cannot actually simplify it into Hg NO3 because we said we use empirical formulas. But here Hg NO3, I cannot do that because Hg2+, as I said, this is how mercury 1 exists, and you cannot change it. Okay, Hg2+. You have to keep this in the as is, Hg2 NO3 all 2. That's the right one. Cesium oxide. Well, sometimes you have to refer into the periodic table, and this is something we need to do all the time. And you will be provided with a copy of the periodic table in the exam, and you need to know where is cesium. You keep looking, and you will find that cesium actually is in group 1. Okay, so it's just like potassium and sodium. So cesium is CS. So cesium is CS plus 1. Oxide is oxygen 2-. When you cross multiply, this is +1, this is -2. You cross multiply like that, and you will find this to be CS2O. That's cesium oxide. Beautiful. No di, no mono, because this is type 1. Cesium is group 1, so type 1. Last one is strontium nitride. Why don't you do that yourself, please? Strontium nitride. Try it, okay? Try it and take a look at the book. As I said last time, you have to practice, okay? You have to practice these questions by looking maybe at the practice exercises at the end of each example. Also do the inline assessments and do the end of question. The more the more questions you practice, the better. Now we are done with ionic compounds, and we move on to molecular compounds. Molecular compounds, they have different naming structure. So as I said, molecular compounds, they're made of covalent bonds, and they are they're referred to as type 3 binary compounds. And examples are H2O, ammonia, CH4, and so on. So these are made by nonmetal with a nonmetal or nonmetal with hydrogen. Okay. The way you name them is you name the first nonmetal, okay, as is. So hydrogen, nitrogen, carbon, so on. And the last one is you add an IDE to it as like it's an anion, which is not, but it's like an anion. And then you provide the prefixes mono, di, tri, and so on to mention the number. Okay? So water is water, H2O. Everybody on Earth knows that. But little people know that this the systematic or the actual name of water is dihydrogen oxide. Dihydrogen because there are 2 hydrogens, and then oxide because it's atom. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Those are the prefixes that used to represent the numbers 1 to 10. Remember, the prefix mono may be omitted for the first element. So that's a rule. So for example, PCl3, because there is only one phosphorus, we don't say monophosphorus trichloride, we just say phosphorus trichloride. That's acceptable. Another one is when I say tetraoxide, that's kind of irritating. So we just replace, we say tetraoxide, okay? So N2O4 is called dinitrogen tetraoxide, but I can say dinitrogen tetraoxide for simplicity. So let's practice that. HI, again, you want to name it. You want to ask yourself, is this ionic or covalent? Hydrogen and iodine. Iodine is non-metal, hydrogen is hydrogen. So this is a molecular compound or covalent. You don't name it the way you named ionic compounds. So you say there's one hydrogen and one iodine. So it's actually monohydrogen, monoiodine, but you just say hydrogen iodide. Because we omit the mono from first one. Iodide always makes one, so hydrogen iodide. If you say hydrogen monoiodide, that's not very wrong, but it's okay. NF3. You can name this nitrogen fluoride, but you make a mistake because nitrogen is non-metal and fluoride and fluorine is non-metal. So they're both on the right side of the periodic table. If you look at the periodic table, this is nitrogen right here. Okay, and this is fluorine. They are all non-metals. So you cannot name it actually nitrogen fluoride. You have to name it nitrogen trifluoride in accordance with the naming of molecular compounds. SO2, that would be sulfur dioxide. Okay, and N2OCl4. Here we have an example of an element with H2 at the beginning. So you have to mention di. So you say dinitrogen tetrachloride, dinitrogen tetrachloride. NO2, that's just like SO2, nitrogen dioxide or nitrogen dioxide. N2O, that's dinitrogen oxide, monoxide. Here we have the nitrogen makes a lot of oxides, NO2, N2O, NO. There's so many of nitrogen oxides, and that's why it's important to name them correctly. So the first one is nitrogen dioxide, the other one is dinitrogen monoxide. Okay, so if you have one element on the right, you must use the mono here. You must use the mono, especially for oxides. Okay. Some of these compounds, they have common names, like water, for example, it's water. Ammonia is NH3 ammonia. There is also methane, diborane, serine. But you can. So these are common names that people. These compounds are not known by their common names, but we still can name them according to the system. Here is an example: PPR5, AS2O5, and so on. So anyway, I have to stop here. We can discuss this in the lecture, but next time, inshallah, we'll continue our discussion with SSM bases, and we'll finish this chapter too, inshallah. So thank you for listening so much, and have a beautiful day.